Can you hear me, Papia?
Yes.
Papia, is the live on?
Yes, it is live on. Should we start sharp 2:30 or we'll wait for some
I think
participants?
we'll wait for having lunch. So can we wait for 2-3 minutes more?
Okay.
Sir?
Yes, we can say 2 minutes. We can wait.
Yes. It's just 2:30 now. Maybe we can start from 3-4 minutes later.
চিত্ত কতক্ষণ বলবে তার উপর
যা হোক হবে, আপনি যতক্ষণ অ্যালাউ করবেন।
আমি না, এইসব ফিজিক্সের লোকেরা করছে।
আমি সেটাই হচ্ছে অড ম্যান আউট।
চিত্ত এরকম মানুষ, ওকে
আমাকেও তো আমি অড ম্যান আউট ঢুকিয়ে দিয়েছি।
চিত্ত এরকম মানুষ, ওকে অ্যালাউ করার কে? ও আমাদের অ্যালাউ করে, কতক্ষণ আমরা শুনবো।
হ্যাঁ,
চিত্ত অনিমেষ বাবুর কি খবর এখন যান কাটিউস?
না না না, স্যার আছেন।
অনেক কাল দেখা হয় না।
স্যার এমনি ভালো আছেন।
আচ্ছা,
এখনকার সময়ও ভালো আছেন বেশ।
আচ্ছা।
দুলাল বাবু তো গোটা কলকাতায় ঘুরে বেড়াচ্ছেন।
তো মাঝখানে একটা সাজ্জাদা চলে, শুনেছো তুমি?
হ্যাঁ 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 হ্যাঁ,
সেটা খুব ব্যাড নিউজ।
এটা খুব খারাপ নিউজ। নাকি অসুস্থ ছিলেন অনেকদিন ধরে।
হ্যাঁ, আমরা খুব ঘনিষ্ঠ ছিলাম একটা সময়।
হ্যাঁ, আপনারা তো
জুলিদির ব্যাচ।
হুম,
জুলি ব্যানার্জি, ওরা এক ব্যাচের। তোমাদের এই পিরিয়ডে ফ্যাকাল্টি রিক্রুট হয়নি না?
না, আমাদের হবে বলে প্রসেস চলছে।
আচ্ছা,
আমাদের সব অ্যাপ্লিকেশন রিসিভ হয়ে গেছে।
আচ্ছা,
পরে বাকি কাজগুলো চলছে এখন।
বায়োতে তোমাদের বায়োসায়েন্সের রিক্রুটমেন্ট হবে? মানে বায়ো আছে না ওখানে, বায়োটেকনোলজি?
লাইফ সায়েন্স, বায়োটেকনোলজি, হ্যাঁ ওখানেও তো অ্যাডভার্টাইজমেন্ট হয়েছে।
আচ্ছা আচ্ছা, তোমার নাম্বারটা আমার কাছে নেই, একটু পাঠিয়ে দিও।
আচ্ছা স্যার, আমি পাঠিয়ে দেব।
কেমিক্যাল সোসাইটির কোনো ফাংশন আছে এর মধ্যে?
হ্যাঁ, কেমিক্যাল সোসাইটি তো খুব কাজ চলছে আমাদের। ডিসেম্বরে তো অ্যানুয়াল কনভেনশন।
আচ্ছা,
21 ও 24।
আচ্ছা আচ্ছা,
সেটাও এবারও ওটা অনলাইনেই হবে।
আচ্ছা,
এবং এখন এবার দেশের 9টা জায়গায় একসঙ্গে হবে প্রোগ্রামটা।
আচ্ছা,
বিভিন্ন ব্রাঞ্চের, আমাদের এমনিতে 7টা ব্রাঞ্চ, তার উপর এবছর অ্যাডিশনাল 2টো ব্রাঞ্চ, একটা অসীমা চ্যাটার্জি নামে একটা হয়েছে।
আচ্ছা,
কমনলি ওমেন সায়েন্টিস্টদেরকেই এনকারেজ করতে ওটা, অসীমা চ্যাটার্জি সায়েন্টিফিক সেশন। আর একটা হয়েছে ইয়ং সায়েন্টিস্ট কনক্লেভ।
আচ্ছা,
আর যেমন ছিল অর্গানিক, ইনঅর্গানিক, ফিজিক্যাল, এনভায়রনমেন্টাল, অ্যানালিটিক্যাল, এরকম ভাগগুলো আছে। এবারে ফিজিক্যাল কেমিস্ট্রি হচ্ছে কলকাতা বিশ্ববিদ্যালয় সায়েন্স কলেজে, ফিজিক্যাল কেমিস্ট্রি, এবং সেখানে কনভেনার আছে নিখিল।
আচ্ছা।
আর ইনঅর্গানিক কেমিস্ট্রি গুয়াহাটি আইআইটি।
আচ্ছা,
অর্গানিক কেমিস্ট্রি খড়গপুর আইআইটি। আর আইজার কলকাতা।
খড়গপুরে কে দেখবে?
খড়গপুর দীপক মাল।
ও দীপক, আচ্ছা।
দীপক বাবু সায়েন্টিস্ট ইনচার্জ। তার সঙ্গে আছে আইজার কলকাতা থেকে অলোকেশ বিষয়। আর খড়গপুর থেকে আছে নন্দী। এবং অ্যানালিটিক্যাল হচ্ছে গিয়ে এমএস বরোদা ইউনিভার্সিটি।
আচ্ছা,
হ্যাঁ, এরকম। আর আপনার এনভায়রনমেন্টাল হচ্ছে আইআইটি রোপার।
আচ্ছা, এগুলো বিভিন্ন দিনে হবে নাকি?
না, ওই যে প্যারালাল সেশন যেটা হতো,
ও প্যারালাল। আচ্ছা,
প্যারালাল সেশনটা ওই 2 দিনে হবে, 22-23। এটাই বিভিন্ন সেন্টারে।
দুলালবাবু এখন আছেন তাহলে?
হ্যাঁ, স্যার তো আছেন এখন আমাদের প্রেসিডেন্ট হচ্ছেন জিডি যাদব।
কে?
জিডি যাদব ওই আইসিটি মুম্বাই এর ভাইস প্রিন্সিপাল ছিলেন।
আচ্ছা আচ্ছা, উনি
তিনি
চিনি না
বলেন।
ওনাকে।
না, উনি আমাদের মেন ব্রাঞ্চের নয়, কেমিক্যাল ইঞ্জিনিয়ার।
আচ্ছা।
এমনি পদ্মভূষণ, সরি
হুম।
পদ্মশ্রী এবং অ্যাক্টিভ লোক।
আচ্ছা।
আমাদের
মৌমিতা, হ্যাঁ
জার্নাল এখন এলসিভিআর পাবলিশ করছে।
আচ্ছা, এলসিভিআর।
হ্যাঁ,
আচ্ছা।
জার্নাল আপনি ওয়েবসাইটে গেলেই পাবেন। এলসিভিআর এর নেওয়া থাকলে ওয়েবসাইটে ফুল কপি আসছে।
ইম্প্যাক্ট কত হয়েছে?
ওটা বেড়ে এখন 0.8 হয়েছে।
0.8 হয়েছে, আচ্ছা।
এই 21-এই গেছে।
হুম হুম। মৌমিতা এখন শুরু করবে নাকি?
স্যার তাহলে শুরু করে দিচ্ছি।
হ্যাঁ হ্যাঁ,
আমার মনে হয় শুরু করে দেওয়াটাই।
2:35 হয়ে গেছে।
Okay, so good afternoon all, especially our distinguished speaker, Professor Chittaranjan Sinha sir, our session chair, Professor Sanjeev Ghosh sir, all participants who are mostly faculty members, students, and obviously our respected Professor Aparajita Bhattacharya madam, convener Professor Vimal Kumar Sarkar sir, and whoever gathered here today for the invited talk on towards design of conductor to superconductor structure and supramolecular interaction. I would like to welcome all of you and thank you for taking the time off to join us this deliberation. So before starting, I just want to go for some important announcement for all participants here. That please write your question in chat box. Participation certificate will be given to all individual students, but for faculty members and scholars, only registered people will be considered. And if students want, they can send me mail, and all the details will be provided in chat box. So it is really a great opportunity for me to introduce our respected session chair, Professor Sanjeev Ghosh sir, who was former professor of chemistry and principal of Presidency College and emeritus scientist, Presidency University, Kolkata. Presently, he is the professor of eminence and advisor to Vice Chancellor Adams University. Professor Ghosh is alumni of Presidency College, Calcutta University, Indian Associations for the Cultivations of Science, Kolkata. He was associated with UC Davis, California during his postdoctoral research. He has visited many institutions all over the world as visiting professor. Among them, I can just mention very few like Caltech, Moscow University. He has nearly 100 publications in international journals and 80 research abstracts in various international and national conferences. So without further delay, I would like to request Professor Ghosh sir to chair the session. Sir, over to you.
Thank you, Papia, for inviting me. Actually, as Chittaranjan mentioned, we are odd man out, not physicists. But anyway, when you have called me, so fine. So let me first welcome our speaker, Dr. Chittaranjan Sinha, who is very close to me for a long period of time. Actually, we know many faculties in Jadavpur University, including him. And today he will be talking on something material science, I guess. But before that, let me introduce Professor Sinha. He is a professor and former head department of Jadavpur University. He passed BSc as well as MSc from Calcutta University and PhD alumni of Indian Association for the Cultivation of Science with Professor A. Chakraborty. And he joined first Bardhaman University as a faculty member. Then he shifted for a very short period to Vidyasagar and then came back to Bardhaman University again, and then joined Jadavpur as a professor in 2004. He has visited many countries. Taiwan, he was a visiting researcher. 2003 visiting professor, 2010 he was a visiting professor in Japan, Singapore visiting scientist in 2007, and Italy international lecturer 2011. He has huge number of publications, which is really, fascinating. 400 plus journals in international repute. 47 students have been awarded PhD under him. It's a huge number again. And Scopus H index 44, citation 6,750. It's really a number. It's an astonishing number. He has lots of projects, obviously. Bcs is a DST, editor of some Indian journals as well as some international journals like current organocatalysis, Bentham Science, and other journals as well. So honorary secretary, Indian Chemical Society for 2016, 2019, 20. And he's guiding this chemical society for a long time. He has got various awards. Of that, awarded Best Chemistry Teacher 2012 by Confederation of Indian Industries and All India Council of Technical Education, selected by Association of Chemistry Teachers and Tata Chemicals. He is a fellow of West Bengal Academy of Science and Technology, and he is rated top 2% Indian scientist as reported by Stanford University 2020-2021. And he received Centenary Lecture Award from Tokyo Institute of Science, Japan in 2005. He's a member of various academic boards throughout, many universities in the West Bengal as well as outside West Bengal. And his area of research, he's an inorganic chemist, but basically is material scientist and works, various material science compounds. Like recently, probably he's working on MOFs, and today's lecture will be also based on MOF, I guess. So with this introduction, I invite Chittaranjan, Professor Chittaranjan Sinha. I usually call him Chitto. So Chitto, please, over to you.
Yes, sir. Yes, sir. Thank you, sir. There are two Sanjeevs in Kolkata, around Kolkata, Sanjeev Ghosh and Sanjeev Bagchi. And
Yes.
both of them belong to physical chemistry. And this
Right.
physical chemistry rather very close to physics. In the today physics program, and Professor Ghosh is chairing my session, and this is a privilege to me. And let me to thank Professor Bimal Kumar Sarkar, who is also my friend from for a long time, from our undergraduate times, and also Professor Aparajita Bhattacharya, who is also my colleague in the university. So at this stage, it is a privilege to me to be a part of this program. And so just I share my slides. I think it is visible to you all.
Yes, yes.
Okay. Okay, today,
Yeah.
Third National Conference on Frontiers of Modern Physics. And my topic was design of conductor to superconductor structure and supramolecular interactions. In fact, this is a very challenging field currently to the energy saving as well as the energy crisis, what in the global aspect we are facing. For example, if one thermal plant, for example, see this Kolaghat thermal plant, it is preparing 100 megawatt electricity for particular region. Say around one industry, they are consuming 100 megawatt and contracted with Kolaghat thermal plant that they will supply one full unit production from Kolaghat station. But whenever the consumers, some of the total consumption, this total consumption is covers to 80 megawatt, not 100 megawatt. The company supplies 100 megawatt power, while the consumers, they utilized only 80 megawatt power. But the 20 megawatt power were gone. Anybody else are snatching out that power from the transmission center, or what happened there? Although everything is all right, there is no snatching of current or nobody is tapping it, everything, still there is some loss of electricity. And this is very well known term, the transmission loss. Because of that power which transmits from production center to the consumer part, during the transmission through some electrical connections, they are discharging, and that transmission loss cannot be resisted. And that transmission loss today, it is one of the challenging tasks to minimize this transmission loss or to completely turn to zero. And that transmission loss may be reduced or may be coming to zero if that supramolecular materials are used as the superconductor. If we go through the conductor, semiconductor, insulator, and superconductor, and the idea of superconductor, if you find the first mooted by Kamerlingh Onnes in 1911, where he had shown at very low temperature like 4.2 Kelvin, even mercury shows the conductivity. And this resistance versus temperature plot shows this superconductor after a particular temperature, after the critical temperature, it shows the superconductivity. And in that superconductivity phase, the magnetic property, the interior magnetic field is also that is coming to almost nil. So magnetic property and this conductivity, both are interrelated, and they are coming to that position when the temperature is decreased. It is because of that electrons, those are responsible for this conductivity as well as the magnetic property. They are relentlessly moving around without any direction. In presence of field or in the conducting process, they are becoming channelized in direction, and that resistance caused by these electrons is the result of this loss, which is, that's why the superconductivity is a very useful process for that the resistance may be minimized. And but in physics, people all knows all this Bcs theory. Bcs theory refers to this Bardeen, Cooper, and Roberts theory about the zero electric resistance given by the electrons in its movement in the lattice structure. Zero electrical resistance below a critical temperature. And this Cooper, BCS, both Bardeen, Cooper, and Robert received Nobel Prize in 1972. Followed by this, that there are many such developments throughout the globe for the development of superconducting material. But surprisingly, the material developed by Bednorich and Muller in 1986, they received Nobel Prize in the next year in 1987 because of very simple molecule, yttrium, barium, copper oxide. Yttrium, barium, copper oxide, high temperature superconductivity, their conductivity critical temperature is much higher. It is around 92 Kelvin. And this type of mixed metal oxides, they may be stoichiometric or non-stoichiometric. And in case of non-stoichiometric situation, the conductivity is much higher. And the structural demand for this type of materials is surprisingly regulates the conductivity. And in case of organic compound, you can find there are many organic compounds. Let me to show you that. Then I will come back to one. Many organic compounds, they are also showing superconducting behavior, that is high temperature conductivity, because of their huge number of pi electrons, conjugated pi electrons. For example, this graphene, graphite, fullerene, or their compounds like potassium, graphite, K3C60, potassium fullerene compounds. These compounds have the better conductivity. Even at low temperature, they are showing this higher conductivity, or they are challenging for the superconductivity. So these superconducting materials have the enormous use in the practical field. And the types of superconductors, they are double layer capacitor, I will tell you later on about capacitors. Let me to take or superconductor. Their use are huge, and all sorts of optoelectronic devices, those are consuming electrical energy. The superconducting materials are commonly has a challenging use in this area. And you know, this graphene serves as a superconductor, and it's mixing of this graphene with some metals, alkali metals like potassium or cesium, rubidium, their fluorine, graphene, all they exhibit the huge conductivity at relatively at high temperature. You see the cesium C60, its temperature is 40 K, while the C60 in presence of CHBr3 chromophore, its critical temperature is 117 Kelvin. That means target of the researchers is to design a room temperature superconductor or high temperature superconductor. The problem is these materials what you are using, the graphene or even some metals, all they undergo some changes with time. And this frustration of these materials lead to design of the mixture of metals as well as the organic components. That is the hybrid materials, inorganic and organic hybrid materials. These materials are showing a challenging task now, particularly for the material chemist. Those are designing many molecules based on their utility, and these are the fields of organic, inorganic, hybrid or composite system. And you see herein, this is an organic compound. This organic part is bonded with the metal to bring these more organic parts together. Thus, if these organic parts are pi delocalized and the bridging unit has the ability to transport electron to the metal center, then there is a chance to transport electrons from one part to another through bridging metal, and that may reduce the overall resistance and may improve the activity, conducting activity. And these hybrid materials, they are of two types: the physical mixture of the components and the chemical mixture. Chemical mixture mainly the coordination polymer or coordination network or metal organic framework. In our group, we are doing some chemistry on coordination polymers as well as metal organic framework, and the structural demand for these molecules showing their conductivity, and this part will be discussed today in this lecture. You know, the coordination polymer is well known to us. The Varner in 1897 who has proposed this concept of the coordination of the ligands around the metal. And the J.C. Baylor in 1964 has proposed that coordination compounds can exhibit the polymer behavior and can transport electrons from one part to the other. And it is equivalent to the organic polymers like polythene. But the difference is that these polythenes or polyethylene, etc., they are the covalent system and they don't have any electrons, while there are some organic polymers also available. The amine polymers, those are the conducting polymers. These conducting polymers, the problem of these organic materials, they are the degradation for several use. While the metal coordinated system, they are very stable, and with reference to the chemical environment as well as in the environment, and also they can have the stability towards any sorts of the chemical stress, physical stress, and can be useful for many aspects. So the aspect of the metal organic framework or the coordination polymer towards this objective. In the construction of this coordination polymers, you need the two components. One is the metal center, other is the ligands. Those ligands can bridge, and these ligands are commonly the organic bridgers. Organic bridgers, and their bridging can have the different geometries. These connectors are of different geometries. Depending on their geometry, the overall construction process being continued. Herein you can see this is one 1D chain the single chain is running. Similarly, two chains are propagating in two perpendicular directions, constituting a plane, 2D coordination polymers, and similarly 3D coordination polymers can be constructed. So these coordination polymers are multidimensional, 1D, 2D, and 3D. Depending on these chains, the chains may interact themselves through the supramolecular processes, and these interactions may lead to the electron transfer through space, while in chain, the electron transfer through bond. So through bond or through space, this electron transportation in the material may be responsible for their conductivity. And the coordination polymers are sponge-like system. If the coordination polymer has a cavity like sponge, then that cavity can accommodate some ions or molecules or even the gas molecules. So these type of coordination polymers are defined as metal organic framework. Metal organic framework has the permanent cavity, and that cavity may be rigid or may be flexible. You can remember the silicate cavity, silicate structures, the natural zeolites that have the also cavity, and this cavity serves as the filtering bed for the metal ions. Thus, the silicate beds resist the movement of heavy ions to the groundwater, thus the groundwater being recharged and purified through when it passes through the silicate cavity. Similarly, the gas absorption, gas separation, and this conductivity, all these properties may be accounted when the metal organic frameworks are used. Even the catalysis, photocatalysis, electrocatalysis, and the different other reactions can also be carried out in the cavity phase. The stimulating process, the stimulating agent may be light, may be heat, may be mechanical change, or even the pressure, or the magnetic field may be a physical stimulating process, where the molecules, those are inside the cavity, may be excited, and that excited molecules may initiate varieties of chemical and physical changes. And when we are talking about the supramolecular interactions, that is interactions beyond the molecule. You know, atoms are associated to constitute a molecular unit that has sufficient stability. And when these molecules then interact themselves, they can generate these supramolecules or supermolecules or macromolecules. So varieties of polymeric materials may be defined. While the supramolecules are the special class of such type of polymeric molecules where the interactions are commonly non-covalent, and these interactions are basically hydrogen bonding, pi interactions, these pi interactions through anion pi or cation pi, or lone electron pair pi, or pi-pi interactions, or CH pi interactions, all sorts of these very weak interactions. They are responsible for the stability of these supramolecular systems in polymers. And the supramolecular idea first mooted by these three scientists who received Nobel Prize in 1987. And Jean-Marie Lehn, last year, Jean-Marie Lehn gave a talk in the Chemical Society program, and he delivered a talk about the varieties of aspects of this supramolecular chemistry. And this supramolecular chemistry has the marvelous usefulness, particularly in the designing of molecular machines. And these molecular machines are being controlled by the physical stimuli, and they are regulated by hydrogen bonding, etc. As you know, this hydrogen bonding, which is responsible for the information transfer in the biology, one progeny to another progeny through this DNA hydrogen bonding interaction. And the weakening of these hydrogen bonds or the addition of the metal ions into it causes the toxicity of the DNA, that causes the DNA breakdown, and also the varieties of disease in molecules in the human being. And how that supramolecular system or the metal organic framework is being synthesized. And the synthesis is very simple one. You collect the metals and collect the bridger or organic bridging unit, and they then allow some physical process. Processes are like solvothermal or hydrothermal or sonochemical, electrochemical, and so on, varieties of processes are known. And these processes are responsible for the synthesis of these materials. And these materials, if you consider it as the metal organic framework, metal organic framework are the coordination polymers with permanent porosity. That is, they have the porous structures. These porous structures have the flexible porosity or the rigid porosity. They can participate in sensing or absorption process, gas absorption, storage, electrical conductivity, catalysis, redox catalysis, and different biological application, drug delivery, photocatalysis, and so on. And today, one of the very interesting storage system for hydrogen fuel. And since you know the green fuel, it is the hydrogen fuel, and even the hydrogen fuel running bus that is being made by Tata, and it will be started shortly in our country, particularly in the mega cities. And these hydrogen storage materials are commonly this metal organic framework. And the problem of hydrogen storage is its transportation and its use, since it is an explosive. So the metal organic framework has the enormous capacity in this direction. What these metal organic frameworks can change the behavior of the molecules with reference to its magnetic or thermal or photochemical, photophysical properties. You see one compound that is a manganese compound, manganese 2 azide breached. This azide can breach in many ways with the metals. This is one type of bridging, this is another type of bridging, and so on. The azide bridging, acetate bridging, these are the common inorganic bridging agents. This bridging agent in manganese 2, you know, manganese 2 of D5 electronic configuration, having highest magnetic moment in the single molecule system. And when it is in polymeric phase, there are 5 unpaired electrons in this manganese, 5 unpaired electrons in this manganese, 5 unpaired electrons in this manganese, and it is continued for a 1D chain. And this number of unpaired electrons, if they join in the process of the magnetic moment, and it is observed, as you see, with changing temperature, magnetic moment increases, and after a certain temperature, its magnetic moment is enormously increased. That is a ferromagnetic behavior is observed at low temperature. This is because of the structure of the molecule. And this structure leads to the remnant magnetism. And you know, these unpaired electrons, if they undergo the opposite spin process, sometimes the structural strain is released by changing the spin direction or tilting the spin, which is known as the spin frustration. And that spin frustration may be responsible for its better or this ferromagnetic behavior. So spin frustration, spin bubbling, and so on, and varieties of spin stresses being developed because of this structural strain. Not going to detail of it, some spin interaction and its geometry is responsible its magnetic moment. When they are like linear one, copper oxygen copper system, this linear one, that is antiferromagnetic feature. If it is the perpendicular one, copper oxygen copper, it is perpendicular to each other. One copper oxygen bond is perpendicular to other copper oxygen bond. Here in the spin is ferromagnetic behavior. That means spin orientation is responsible its magnetic property. In metal organic framework, the structural strain may be responsible for this type of spin change. And that spin change is being used in the charge transportation process, and the charge transportation through bond charge transportation and through space charge transportation. When the metal organic framework, you see, just consider the Prussian blue. In Prussian blue, you know, iron is breached by cyanide. One iron 2 is breached by cyanide to another iron 3. Iron 2, cyanide, iron 3 bridging. So one electron may come from iron 2 to iron 3 through cyanide bridge. Thus, the charge transportation, metal to metal charge transportation is responsible for its long range electron transfer process. Besides that, this bridging group, if bridging group is redox active, then this group may participate in the charge transportation, not through bond, but through space. So through bond, through space, charge transportation may be responsible for the higher conductivity of this type of materials. And in metal organic framework, the structural strain over this transportation process is observed, and the conductivity is enormously changed. And these type of fields are now very challenging, and many group of scientists are working. Just you can see the number of publications per year. And in 2020, the number of publications even doubled than 2018. And the publications include varieties of charge transportation process, and they may be through bond, through space, or extended conjugation, hopping, gas promotion, and so on. And all these processes are responsible to change their conductivity, magnetic property, that is property, those are dependent on electron spin, as well as the property, those controlled by the resistance of the electron. Not going to the detail of the, I have very limited knowledge on physics, so I can't say you many things about its conductivity. Only I can tell you about the designing principles and the utilization. These are the different types of cyclic voltammograms. Those can be useful to interpret what type of interactions are being occurring in the material. Okay, let me to come to this is one molecule. See, in this molecule, aromatic amines, these amine molecules, they are being coordinated with nickel, and this macrocycle is generated, which is also a metal organic framework. This metal organic framework has the cavity dimension is around 1.5 nanometer. In this cavity, when a charged species comes inside the cavity, its energy is much higher than that of the charge which is running through the bond over the metal organic hybrid system. I mean to say, when charge carries through nickel to organic group and so on, and this charge transportation and charge transportation from this organic molecule to this organic molecule through space are quite different. And when charge entered into this cavity, its energy is quite different. And that is interpreted in the capacitance property of the material. And we have designed some molecules. Those are the coordination polymers. Sometimes they are also metal organic frameworks. You can see here is one cadmium compound. Cadmium, one of the important constituent of electrode material. Or we are using this cell phone where the battery is made up of nickel cadmium battery. Today it is being replaced by lithium battery or some other batteries. And commonly this cadmium, here in the bridging material, this is one bridging material having this oxygen and nitrogen bridge. This is a hydrazone. And here is also pyridine nitrogen that can also bridge. This is isoniazide. Isoniazide, a molecule which is used as a drug, particularly for the TB patient. It is a TB drug. And this isoniazide can bridge cadmium along with, this is a dicarboxylate, 1,4-benzene dicarboxylic acid. Here is one carboxylate bridging agent. There is another carboxylate. Thus, isoniazide is bridging cadmium center, and this benzene dicarboxylic acid also bridging cadmium. Thus, it generates a coordination polymer, and that coordination polymer has the permanent cavity. That's why it is a metal organic framework. And this metal organic framework has the dimension. You can see the distance is around 4 angstrom, 3.575 angstrom. And this is around, say, around 39%, 39.8% accessible void space in the overall space. You see, the molecule contains some solvent. The solvent molecules are placed in the cavity. On heating, these molecules are removed, and the cavity becomes free. And this cavity is now available to absorb some molecules or ions. And one such absorption is the iodine. It absorbs iodine, you see. You take a iodine solution, you take iodine solution in cyclohexane and add the crystals, and then these crystals absorb iodine, and you see after 48 hours the supernatant becomes clear, almost going to be clear, and the crystals are being colored. Thus this crystal absorb iodine, and this iodine which is absorbed in the crystal cavity, they are also being removed on heating or treatment with ethanol. On treatment with ethanol, gradually you can see with time the iodine which is absorbed by our molecule is being removed, and after 80 minutes it is also free. And also just by washing you can get that free molecules which reabsorb iodine. Okay, this is the property of the our molecules which have the cavity that can absorb iodine, and the cavity is also its volume is being cavity volume is measured by the BD process, the nitrogen absorption studies, and this molecule is being used for its conductance measurement, and this conductivity measurement shows in absence of iodine, the band gap is around 3.48 electron volt, and in presence of in presence of solvent, in presence of solvent, this band gap is this one, and in presence of iodine, this band gap is 3.19 electron volt. So this band gap is decreased when iodine is absorbed, and this band gap leads to the conductivity. You see, the molecules which is activated, this activated metal organic framework shows the conductivity at dark phase. It is around 5.14 × 10⁴ Siemens per minute, while on light radiation, its conductivity is increased. And similarly, the iodine adsorbed molecules or the polymer, this iodine adsorbed polymer, its conductivity is slightly higher than that of the conductivity of non-iodinated system. Thus, the role of iodine has also some importance in this regard. And the photosensitivity of the molecule also enhanced upon absorbing iodine. And this photosensitivity leads to decrease in, you see, the iodine absorption leads to decrease in the barrier height. Barrier height in the dark phase is around 0.312 electron volt, while in the light phase it is decreased to 0.289. While the iodinated system, its dark phase barrier height is 0.293, while the light phase is 0.266. That means both iodinated phase and non-iodinated phase solvent-free system, both are active towards the light radiation to show its conductivity as well as the resistance. But you can see the resistance, the barrier height, that barrier height is also decreased from 540.96 ohm in the dark phase to 22.68 ohm in the light phase for the molecule, which is the activated molecule, while the iodine absorbed activated molecule, its dark phase resistance is 451, which is decreased, and the light phase is much reduced to 262.83. That means the molecules on iodine adsorption enhances its conductivity, reduces its barrier height. And this has been instigated us to design many other molecules using many connectors. Herein we change the carboxylate bridging group with reference to the succinic acid, fumaric acid, and this also 1,4 benzene dicarboxylic acid with zinc as the node. That the metal center, instead of cadmium in previous one, we use zinc using 3 different types of carboxylates, while isoniazide is the same. And this leads to three different compounds. These three different compounds have the different barrier height, and this barrier height leads to the different conductivity pattern. So the metal coordination, metal remains same in three molecules. Only the bridging group, bridging carboxylates are changed. And bridging carboxylate shows this one, that is the succinate derivative, shows the better conductivity since its band gap is the lowest one amongst three. And this insists, you see the change in the current voltage diagram. Current voltage diagram in the dark phase as well as in the light phase. And this is for the light phase, while this is for the dark phase. Light phase conductivity, you see, light phase conductivity and the effective mobility, all these things are shown here. And we have three molecules. One is the succinic, second is the fumaric, and third is the benzene dicarboxylic acid. The charge transfer resistance is the lowest one in the succinate derivative. And that is also reflected from the Nyquist plot. This diameter of this Nyquist plot can give you the ability of the charge transference ability or the barrier height, or one can say the resistance. The resistance is the lowest one in case of the succinate derivative, this one, followed by the fumarate and 1,3,1,4 benzene dicarboxylate. So all these support there's a dark phase and light phase conductivity of the molecules. Herein we are using this acetylene dicarboxylate derivative. Hence acetylene dicarboxylic acid and the succinic acid. Difference is that in acetylene dicarboxylic acid, structurally it is linear. Besides, it is conjugated one. It can participate in the charge transportation process. So this linear charge transportation process, and while the succinic acid, it is a non-linear type, but charge transportation can be carried out through space. So through space and through bond, both are being possible for the acetylene dicarboxylate derivative, but only through space is feasible for the succinic acid. So these two molecules having the two geometries, they have the different conductivity. And this conductivity difference because of their structure as well as their bridging group behavior. So the conductivity depends on the several factors. Commonly, one is the structure factor, other is the Maitland factor, third is the bridging group factor. And in the bridging group, you know, the bulkiness in the bridging group, the communication amongst the bridging group, as well as the atom size, electron density, pi acceptability, etc., can regulate this property. Okay, not going to the detail it, only thing that upon light radiation, this band gap is decreased, and that enhances the improvement in the conductivity. Herein we use another series of molecules, that is to increase the number of conjugated electrons in the bridging group, anthracene dicarboxylate. Anthracene dicarboxylate also initiates this charge transportation, and it shows a very interesting behavior because of this pyridine. This pyridine naphthyl system is here. This pyridyl naphthyl system. This pyridyl naphthyl system has another property. That property is the sensing property. While you see in the three-dimensional structure, remove it. In the three-dimensional structure, you can see there are pi-pi interactions, CH-pi interactions. All these are the interactions responsible for space charge transportation. And besides the space charge transportation, this molecule, this three-dimensional views having the pi-pi interaction, this pi cavity attracts metal ion. Here in this pi cavity attracts the metal ion, and thus the chromium 3, only chromium 3 plus gets position in this pi cloud, and thus it becomes a chromium sensor. Upon addition of the different metal ions, only in presence of chromium ion, it shows the sensitivity. That is this coordination polymer is useful for two purposes, one for the conductivity measurement, other for the sensing measurement. So not going to the detail of sensing study, since our interaction mainly on the conductivity. This conductivity is increased in the light phase. You see, the light phase resistance is almost half to the dark phase resistance. Dark phase resistance is 135 unit ohm, while the light phase resistance is 76 ohms. So in the light phase, the molecules becomes more efficient for conductivity study. Okay. Here you see another molecule. Here this molecule has the beauty of this thiophene carboxylic acid. This thiophene carboxylic SH and COOH. During the complexation process, this thiol group undergoes the SS coupling reactions, which is very common in presence of air oxygen. This thiol sulfur is oxidized to form the sulfur-sulfur bond. And this leads to the sulfur-sulfur bond, and this carboxylate bridging. This is a carboxylate bridging group, and this carboxylate bridging through sulfur-sulfur bridging motif. This motif has very interesting behavior upon light radiation, where the conductivity is enhanced. Herein, upon light radiation, this sulfur-sulfur bond clips. Herein you see the cartoon picture shows this sulfur-sulfur bond clips, and thus molecule dissociates. If you irradiate with, if you aerate it, or if you pass air oxygen, then again reoxidized. It is also reduced by sodium borohydride type reagent, or can be reduced by electrochemically. That also leads to the cleavage of this bond, and that cleavage will lead to that cleavage is responsible for its molecularity and is responsible for wording of conductivity, what we could expect, but we are not achieved at that point because the energy is being used for sulfur-sulfur cleavage. And its conductivity, you see this conductivity at the light phase is increased, but theoretical conductivity is much higher than that of the experimental one, because this energy is being used for the sulfur-sulfur cleavage. Besides the plot of log I by log V, and the potential current plot shows three different regions. You see, the region one is responsible, which is the common relationship, that is ohmic relation between current and voltage, where the I varies as V, while in the region 2 and region 3, current is increased, and it is not a simple V varies as I. Rather, here V varies as I square in case of 2, and in case of 3, it is V varies as I to the power 2.6. So, at the region 2 and region 3, what we find, the huge current development. And this huge current development, because of some improvement in the space charge conductivity in the molecule. Hence, the bond conductivity is responsible for the current voltage relationship in the ohmic range, while the space charge transportation may be responsible for extra enhancement in its current. So this is one of the important area of the designing of molecules. Okay, it is also similar type of molecules produced by acetylene dicarboxylate with the pyridyl vinyl system, vinyl pyridine, and it shows the two regions in the current voltage diagram, the similar type of Nyquist plot, and the current is improved beyond the ohmic point, and the current potential relationship is V varies as I square. So our target is to design the molecules. Those can give us the current, unexpectedly very high current, or the better conductivity. Herein also, this molecule also shows similar behavior, not going to in detail. Rather, our target is to design the molecules by changing the metal center, by changing the bridging unit, as well as its conjugation, and also the interaction pattern, electron donating, withdrawing groups, etc. Those you can monitor its conductivity. Herein, we use nitroisothalic acid. This is an electron withdrawing group. This electron withdrawing group has the capacity to regulate the electron density movement into the molecule. And this, at one hand, it forms the zinc complex, on the other hand, it forms the cadmium complex. The zinc and cadmium, only the change of metal ions have changed the entire character of the complex system. You see, herein the polycatenated system is 2D plus 2D type. 2D plus 2D polycatenated diamond-like topology, while this is a polycatenated 4 square grid type networks. So the size of the metals, zinc to cadmium, cadmium is the 4D and zinc is 3D. So size of cadmium is increased. That changes the feature of the framework, and thus the characters, every character will change. So not only the nature of the metal ion or the bridging molecules control the conductivity, rather the structural pattern also controls the conductivity. Herein also we find the conductivity, and cadmium has the better conductivity than zinc system. It is because of the 4D orbital, which is more delocalized. That may be the reason for enhancement of conductivity in cadmium system. But you see the band gap in cadmium compound is much less than that of the zinc complex. Band gap is 2.77 electron volt in cadmium, while 3.21 in zinc. Okay, the current voltage relationship also in the similar pattern. The first phase follows the ohmic relationship, while the second region does not follow ohmic relationship, which is known as the Schottky diode type behavior system. And also the dark phase, light phase activity is similar to earlier, not going to detail of it. Okay. Herein, another interesting feature, light radiation, photoactivation of the molecules. Photoactivation enhances the conductivity. Again, that light energy may be used for some other chemical reactions. Herein, this vinyl naphthyl pyridine derivative, this pyridine derivative of cadmium complex brings this olefinin double bond very close to each other, less than 4 angstrom. In the structure of the molecule, the two olefinic double bonds are very closely spaced, less than 4 angstrom, and light radiation leads to CC coupling reactions. So this CC coupling reaction gives a system who is saturated one, so the conductivity of the charge conductivity is somehow restricted in case of these cyclobutyl polymers than that of this olefinic polymer. This olefinic polymer shows the better conductivity than that of this cyclobutyl polymer, and it is being observed from this current voltage diagram, and also from IQ's plot, and from other directions. Herein you can see the same thing, cyclobutyl derivative, and at the current voltage diagram, log I log V, some part at the inflection point, and after that the Schottky diode behavior is observed, but its mobility is quite less than that of the previous one. Herein another molecule also shows similar type of behavior along with some sensing behavior. This molecule, naphthyl vinyl pyridine system, this naphthyl vinyl pyridine system shows this conductivity along with the sensing activity. It senses only group 3A metals, iron, chromium, and aluminium, but cannot distinguish them. So it is not so much interesting since the three metal ions are being not being distinguished by the molecule itself. Okay, the same type of system. This is some zinc complex, but the difference is that herein we use the terpyridyl blocker. Terpyridyl blocker with the carboxylate bridging system. Zinc terpyridyl blocker, the terpyridine having the huge number of pi electrons and also the molecule is pi acidic. So we expect the better conductivity and we also observe the conductivity. This is the in presence of light. You see that the dark phase, it is also almost non-conducting, while in the light phase, its conductivity is enormously increased. And the light phase, this conductivity change is also recorded by current voltage relationship, where you see there are three regions. Region 1 for the common ohmic, while the region 2 and 3, they are the Schottky diode behavior situation. And interestingly, the molecules, the photoconductivity of these cadmium molecules, herein, this cadmium molecule, it shows a macrocycle system, metallomacrocycle. You see this metallomacrocycle. As if this metallo